discussing the seismic analysis procedures, and we started actually discussing the equivalent lateral force procedure as prescribed in ASC 7-16 or IBC 2021 or BCP 2021. So we first had a quick overview of all the available seismic analysis procedures, so that we understand what we are discussing actually, in which domain we are talking. So we know that now there are 4 broad categories of seismic analysis procedures: linear static, linear dynamic, non-linear static and non-linear dynamic. So obviously the non-linear dynamic analysis is the most accurate seismic analysis procedure, in which the computer model used to analyze the structure is capable of predicting any damage, and at the same time the seismic loading is idealized as a dynamic loading, right. On the other hand, we have linear static analysis, where the computer model used for analysis is linear. It is following the Hooke's law forever, and at the same time the applied loading, seismic loading, is assumed as a static loading or is represented as a static loading, right. So the ELF procedure is in this domain, linear static analysis. So we use a linear computer model here, and we apply some static forces which are representative of the future earthquake loading to our model. So in all this, that linear domain 1, 2, 3 and 4, in all those 4 methods, there is a concept of R factor, right. So the pure elastic seismic forces which are calculated by these 4 methods, we reduce them by an R factor, right. And the intention of that R factor is that our structure can be allowed to go in nonlinear range, a safe nonlinear range, relying on its ductility and overstrength, right. So how we can allow them to go in nonlinear range or safe nonlinear range? By providing a capacity which is lesser than what is required, right. So we divide the elastic force demands produced by the applied loading, we divide them by a reduction factor called R factor or response modification factor. The more a structure is ductile, the more we can rely on its ductility and useful properties. So which means the higher R we can use for that particular case. We can design that on further reduced forces. For very ductile type of structures, this R can be as high as 8, right. So if you can say the design force of a particular column against a particular earthquake calculated by any of these first 4 methods, if it is, let's say, 800 kilonewton, you will be designing that column at just 100 kilonewton. You will be providing the reinforcement and cross section size corresponding only to 100 kilonewton, as though the applied action is 100 kilonewton only, right. And that cross section and reinforcement will be sufficient for that action which was otherwise capable of producing 800 kilonewton force, right. But that was if the structure were linear elastic, right. But now we provided less capacity and we make it very ductile. So now it will go in nonlinear range when the real earthquake will hit, but that real earthquake will not be able to produce 800 kilonewton now, right, because the path which our structure will follow will not be linear now. It will deviate from linear, and that deviation we will be keeping in the allowable range or safe range, right. So if it can follow that deviated path without losing its load carrying capacity, then we are safe, right. So this is the seismic design philosophy in a nutshell if we are following first 4 methods, right. In ELF procedure, we directly reduce the applied forces by the R factor. So it's not that we apply full force and then reduce the response by R factor. we directly reduce the applied force and calculate the response against reduced forces directly, right. Since the model is linear elastic, so it is following F is equal to KU, so it's same thing, right. So either we apply a full force and then reduce the response, or we just reduce the applied force first, same thing. Model is linear, so it will follow a linear equation, F is equal to KU. So then there are some additional considerations when you apply that equivalent static force, reduced force. After that, there are some additional considerations which I will quickly go through today. In the nonlinear domain, we again have two categories, linear, nonlinear static and nonlinear dynamic, right. In 5, 6, 7, actually 6 and 7 are same method, nonlinear dynamic method, but the calculation algorithm or procedure is different. Similarly, 3 and 4 is same method, but calculation procedure is different. So in nonlinear methods, you don't need R factor, because the model itself is capable of following that deviated line itself. No need to, implicitly apply different factors to account for nonlinearity. It will be accounted explicitly in this domain, right. So no need of any code factors. Whatever demands you get from these methods, they are directly the nonlinear or design demands, right. They are directly the demands which you can use. No need of further modification. So we already started this ELF method, and we have seen how to calculate the equivalent lateral forces and how to distribute them along the height. So we started with calculating the time period, approximate time period, right, and there are 3 different expressions, and then there is an upper limit on approximate time period also. And if the modal analysis time period is available, then there are different cases. In some cases we should go for modal analysis time period, in some cases we should go for the upper limit, right. So if the modal analysis time period is not available, in that case you only have these 2 things, right. So just check, just use TA then, right. So the first case is, if the modal analysis time period is not available, then you don't have any option but to use the code formula to calculate TA. If it is available, then you have further 3 cases. So sometimes in one case you use upper limit, in one case you use the modal analysis, and in the other case you can use the TA. So then you go for the calculation of seismic weight and then the base shear coefficient, different expressions for base shear coefficient. There is a main expression, but then there is an upper limit and then there is a lower limit, right. So in some range of time periods, which means in some range of the building heights, your main expression is going to govern this range. After that, maybe the upper limit is going to govern this one, and after a certain time period, lower limit will start governing, right. So you can do that experiment yourself also, that vary the time period on x-axis, and then for some real set of values of SS and S1, check in which time period range the main equation is governing, in which time period range your upper limit starts governing. Upper limit starts governing means that the main equation is giving a value which is higher than the upper limit, so you will use only the upper limit. And then after a certain time period, you will see beyond a certain time period, maybe from this onwards, lower limit will start govern, right. So when the building is very flexible, the main equation will give a number which is lower than the lower limit, so the lower limit will start governing, right. So in general, stiff buildings, low time periods, upper limit will govern. Flexible buildings, large time period, lower limit will govern, right. Same was the case in the UBC 97 also. There were upper capping and there was a lower limit, right. So please keep those limits in mind. In this regard, I forgot to tell you, actually it was my mistake, that I was saying that you may use a different model to calculate a different time period actually, and use a different time period. I missed that option, that why not to make another load case, as mentioned by someone from you, that why not make a different load case within the same model, and the software allows you to give your own time period also to be used in ELF procedure, right. So you can use a different load case to use a different time period, and another load case for a different time period. For example, we know that for computing drifts we should use T computed without the upper limit, right. So for drift, if you have the model analysis time period, use that time period, right. But for calculation of forces, you should use the upper limit CUTA. So which means two different time periods, one for calculating forces, one for calculating drifts or displacements. So you can make two different load cases within the same model and give two different time period options in those cases. So you can get the force results from one load case and displacement or drift results from another load case within the same model. So there may not be need of a separate model, as I have said in the last session. Then vertical distribution, we discussed that already. For low time periods, which means low rise buildings, the distribution formula is such that it will roughly give you a triangular distribution if the story heights and story weights are almost constant. So this will correspond to the fundamental sway mode shape for low rise buildings. For high rise buildings, the expression coefficient is such that it will give you a parabolic distribution, because the first mode shape for high rise buildings is parabolic. The intention is to apply a loading pattern such that it deforms the structure in a shape which is contributing to the dynamic response the most, right. Since the first mode shape contributes the most, so we select a pattern corresponding to that, right. So there is a horizontal distribution of forces also that is automatically handled when you are using a commercial finite element based program. Now some additional considerations once you apply forces and calculate response. The first one is the inherent and accidental torsion. First, inherent torsion. If there is for example, rigid diaphragm option you used, this is your rigid diaphragm, and if there is an eccentricity, which means some difference in the location of center of mass and center of rigidity, which means the whole resistance of your diaphragm is concentrated at another location, and the whole mass is concentrated at another location. Center of rigidity means that whole stiffness, the resultant of that whole stiffness can be assumed located at this point, right. So if these 2 points are located at different locations, then obviously the applied forces will produce a torsion in your diaphragm, right, and that torsion will be equal to the force applied at that diaphragm multiplied by the eccentricity between center of mass and center of rigidity, right. So this is inherent torsion. The structure's geometry and configuration is such that this torsion is already there in your structure, right, inherent. On the other hand, you also have another kind of torsion, that is accidental, which means, as the name indicates, that if due to construction issues or some other you can say practical reasons, if there is an difference between the center of mass and center of rigidity as produced by any construction issue, practical issue, then it is accidental torsion. That product of force times that eccentricity will be considered as an accidental torsion, right. So, it is an additional, you can say, force or additional moment which is applied to your diaphragm or your floor in order to account for those accidental scenarios which can cause additional torsion, right. So, there is an inherent torsion which is there, you know that exactly how much it is, and there is an accidental torsion which you cannot estimate, because it can be caused by any reason which currently may not be known, right, in future. So, there is a method to account for that accidental torsion as well, and that is just assume an accidental eccentricity, right. Just assume that there is a 5% difference between these 2 points, and that additional moment, accidental torsional moment, is included in the analysis, is included in as the applied action, right. So, that will handle your unforeseen accidental torsion cases in future. So, for rigid diaphragms and inherent torsion case, the distribution of lateral forces at each level, which is this one, horizontal distribution, shall consider the effect of inherent torsional moment resulting from eccentricity between center of mass and center of rigidity. So, when you allow a computer program to automatically apply the horizontal distribution and you use the rigid diaphragm option, this one, the program will automatically include the accidental torsional moment, inherent torsional moment in your analysis, right. But for flexible diaphragms, the program will divide the force, because you know in case of rigid diaphragm, you know that one force per story, because it is all rigid, right. So, it is applied only at center of mass. So, if the center of rigidity is somewhere different location, whatever is the actual eccentricity, that will be, the moment will be produced automatically when the force is applied at center of mass, right. So, for rigid diaphragm case, the inherent torsion is simply the story force applied multiplied by the inherent difference between center of mass and center of rigidity. But for flexible diaphragms, program does not apply one force per diaphragm. It actually distributes between different vertical elements at that story, columns, shear walls and other elements. So, for flexible diaphragms, inherent torsion is accounted by distribution of forces to the vertical elements, and the location of that vertical elements will be real location. So, whatever is the effect of inherent torsion will automatically be accounted, right. So, the program will divide it to different elements and based on their stiffness obviously, and whatever is the net effect of inherent torsion will be accounted by this distribution to different elements, right. So, summary is that for inherent torsion you don't need to do anything. The program automatically can handle it for rigid diaphragm as well as for flexible diaphragm. So, you only need to just provide a 3-dimensional model and program will handle that thing. So, you don't need to separate out the member forces, right. Like this is the member force without considering inherent torsion and this is with considering inherent torsion. No need to do that. Automatically it will be accounted when you when you use a 3-dimensional model. So, let us say this is the plan view of a diaphragm and Vx is the story force calculated by the ELF method, right, for this particular story. P1 is, let us say, the center of mass and P2 is the center of rigidity, and x is the eccentricity in the perpendicular direction of the applied loading, right? So if applied loading is in the x direction, we should consider the eccentricity in y direction. So let's say it's small x. So mtx, which is the inherent torsional moment, will be automatically included in the analysis, which will be simply Vx times small x. Small x is the eccentricity. And after the analysis, by the way, you can check for all the diaphragms, you can check what is the eccentricity. Program calculates these 2 points and gives you their location, so you can measure exact eccentricity which is there. The second type of torsion is accidental torsion, and it is the moment caused by assumed displacement of the center of mass each way from the actual location by a distance equal to 5% of the dimension of structure perpendicular to the direction of applied loading. So code handles this situation that it gives you a minimum eccentricity which you should always consider even if there is no actual eccentricity. So even if the center of mass and center of rigidity are exactly same point, perfectly regular building, in that case the inherent torsion will be theoretically 0, but still you need to consider accidental torsion, and that is the code provides an eccentricity of 5%. 5% of the dimension of diaphragm in the perpendicular direction of the applied loading. So if I am applying Vx in the x direction, and capital B is the dimension of diaphragm in the y direction, then 5% of B either way, upward or downward, positive or negative, right? So 5% upward and 5% downward. So you will make two cases: accidental torsion moment, where you apply Vx with the 5% of the B in clockwise direction. Clockwise means you are using this point, you are considering that your center of mass is this top point, right? And second case, when you are considering this point 5% in negative direction, in this case it will be counterclockwise accidental torsional moment. So 5% eccentricity is the minimum you should always consider in order to account for accidental effects, torsional effects. When the earthquake forces are applied concurrently in two orthogonal directions, the required 5% displacement of the center of mass need not be applied in both of the directions at the same time, but shall be applied in the direction that produces the greater effect. So it's not that you apply eccentricity in both directions in one case. You make this as a separate case of applied loading and this as a separate case of applied loading. So actually this Vx need to be applied 3 times separately. One at the actual center of mass, one at a 5% positive eccentricity from the actual location, and one 5% in the negative eccentricity of the actual location, right? So all 3 red dots, one by one you should apply Vx and then run the analysis, run the design and consider the critical case, right? So generally how we handle this situation, that if we have one load case in which earthquake is included, we convert it into 3 load case. In one case we use this particular load case, in one combination we use this one, and other one we use this one. So we divide our load combinations into multiple combinations. Actually we multiply them into different further combinations. E-tabs actually allow us to apply all 3 cases, actually all 6 cases, 3 Y cases also. All 6 it allows us to apply in the same load pattern, right? But actually in you can say at the back end it is applying all 6 forces one by one, right. So it is creating multiple sub patterns in that main load pattern, right. So if we check x and y together in the same pattern in ETABS, it doesn't mean that it is applying them together. It is still applying x separate and y separate, right, and then it will be reporting the results for both sub patterns separately. So currently we know that the equivalent lateral forces we can calculate, and then we can distribute along the height, and then the next thing is that we check the accidental torsion, right. Not check, actually we should know that there is an additional effect or torsion which should be included, and that torsion have two types, inherent and accidental. Inherent is automatically accounted. Accidental you have to account by providing this eccentricity, by actually telling the program that apply the force at a not exactly at the center of mass, but at a distance from that, in positive and in negative, right. But this point is saying, last point, that you should not apply the eccentricity in x and y at the same time. You should apply x separately and y separately, and whichever is producing more force, use that for the purpose of design, right. Then there is an additional consideration, and that is amplification of accidental torsion. 5% eccentricity is provided by the code itself as a representative of the accidental torsional moment. But there is a case when you have a type 1A 1B irregularity, and at the same time your seismic design category is D, E or higher seismic design category. In that case you have to multiply a torsional amplification factor, this one, to your accidental torsional moment, right. So whatever you calculate Vx times 0.05 time of capital B, which you see in the last slide, you again have to multiply with a constant Ax, which has a value between 1 and 3, and that value is calculated using this expression, right. And that expression is using the value of average of the displacement at the extreme points of the structure at particular level, computed using Ax equal to 1. So first you don't apply this torsional amplification factor, and calculate your displacement values or drift values at the corners, and that corner should be the perpendicular direction of the applied loading. So if you are applying forces in this direction, calculate the delta A at this corner and at this corner, right, and take their average also, and then divide the maximum of these two, delta A and B, with the 1.2 times of average, take its square. This will be your accidental amplification factor. If it comes out to be more than 3, use 3, right. So you can guess by the construction of this expression that if due to the application of lateral force, this one, if the building tends to rotate, and that rotation is actually quite high, such that it is more than a particular limit, and if your building is irregular, your seismic design category is D and above, then you should calculate this Ax factor, right. So it is a ratio of the maximum displacement by the average of the displacement at the two corners. The summary is, if your building is rotating too much, increase your accidental torsional moment used for the purpose of design. So first you apply accidental torsion and don't apply any amplification factor, and check this thing, right. Actually the results of that initial application of accidental torsion load case will give you whether you qualify to apply for AX or not. And that is actually, I should have mentioned that exact provision here, but if I can remember correctly, it is that if you have type 1A 1B irregularity and at the same time you have a seismic design category D plus, right, D, E and above, right. If you have this condition, then you calculate AX and then repeat your analysis including AX, right. So in order to check whether you have that type 1A 1B irregularity, please remember that there was a criteria for checking that also, and that criteria was also in terms of these delta A, delta B and delta average, right. So please go to that horizontal and vertical irregularities table and check whether you have that 1A 1B irregularity. If you have that, then come back here and calculate accidental torsional amplification factor and apply that factor to your applied loading, right. Then story drift determination. Let's quickly see this thing because this is related to the application of that CD factor, and then we continue tomorrow. So in this figure you have two deformed shapes for this example frame. One is lower level of deformation, which is represented by dotted line under the lateral applied forces, ELF forces, and the solid line is a higher level of deformation, right. The dotted line is actually the deformed shape of this frame under the reduced forces, design level forces. Elastic forces reduced by R factor already, and then because when you apply reduced forces you will get this dotted line deformed shape. But you know from the preceding discussion that this dotted line deformed shape doesn't correspond to the actual deformation which the design earthquake is going to produce, right. What we did is actually that this is the level of force, elastic force, which the design level earthquake is going to produce. If we provide enough capacity for the structure to remain linear up till this level VE, the structure will follow this line and the resulting deformation will be obviously this one. So this deformation is the actual deformation which the future earthquake is going to produce in your structure. But what we do, instead of applying VE, we apply VE over R, right. We apply VE over R, which means that the analysis will give us a displacement which is this one, right, and not the actual. The earthquake is going to come. It is not, when we say VE over R, it is not that our design earthquake is going to have a reduced magnitude. It will come anyway. We are providing a capacity less than what is required, right. So when an actual earthquake will occur, our real structure which is designed on VE over R, it is going to follow this line, this deviated line. Beyond VE over R, it will start showing some symptoms of nonlinearity because it is not given a capacity more than that, right. So based on its own ductility and overstrength, it will deviate from straight line. So it will follow, in the real earthquake, it will follow this deviated line and it will reach to almost the same point in which our original elastic hypothetical structure would have reached, right. So in order to shift this point, which is the analysis output of displacement from the reduced forces, in order to shift it from this to this point, we multiply with CD factor, right, and CD factor is slightly less than R. If R is, let's say, 8, it will be 5.5, or if R is 6, it will be 5, for example, right. So roughly you will reach to the same displacement point when you apply CD only to displacements, right. So this solid line actually is the deflected shape when CD is applied. It is the amplified deformation of the structure the actual non-linear deformation, right? So you apply this to displacements also, and you also apply to drifts. Drift is calculated from displacement. So if you apply it to, for example, elastic displacement, then the resulting drift will automatically be amplified, right? So here you see this some notation, for example, delta, small delta E is the deflection due to the elastic forces, reduced forces, and when you multiply with CD over I, it becomes delta 1 or delta 2, which is the actual non-linear. So this is based on VB over R, and this is based on after multiplication by CD, right? So this delta 1 and delta 2, two deflections of 2 stories, these we will be using to do any decision making on design, right? The amplified forces, not the original, amplified deformations, not the original deformations given by the reduced forces analysis, right? So there is a check on that the capital delta, which is the inter-story drift, the difference of the deflections, amplified deflections of the 2 stories, that capital delta should be less than an allowable value, and that allowable value is actually prescribed in 12.12-1. So actually you have to calculate all the story drifts for all your stories and check against the allowable values, right?